hyperbolas. X, y, and xz are going to have hyperbolas. And so it's going to look, let me see what's the best way to draw it. It's yz. Okay. Yz. It's going to be like this. So it is like taking a hyperbola and rotating it, but in a different way. Like this. So z and y. That's right. That's right. So so this is now actually I'll draw the coordinate system because it's not going to mess up the picture too much. So this is x, y, z. So this is these two things are hyperbolas. This and this are the two branches of the hyperbola, which is it includes z and y. Oops. I know I didn't do it right. I didn't do it right. Yeah. Okay. And you can tell. It's in, what I wanted to do. You see, what you have in my picture, x and z. If you look from the point of view of x and z, then you get ellipses. So x and z should have the same sign, and not so it's like this. All right. So the hyperbola, this hyperbola is in a zy plane. So to get it, I have to just retain the z and y part of the picture, and that's y squared. Did I get? And I got this part right. Okay, at least that's good. So this is x equals 0. You see, so this is the case when x is equal to 0. I just said x is equal to 0. I get this, and that equation is a red one. That's this one. Okay. Again, I don't have time to explain the detail of this. You'll have to figure this out. Why it's like this, and I will draw you one more picture because we have to also tackle paraboloids. And there are two types of paraboloids: an elliptic paraboloid and a hyperbolic paraboloid. An elliptic paraboloid is kind of easy. It's just like rotating the parabola around the z-axis. But the really cool one is a hyperbolic paraboloid, and that one's the hardest one to draw. I used to do very good pictures of that one. Let's see if I can do it. Okay. Let me just draw it and then we'll move on. Okay, that's one. And another one. You see? So it's like this. So it's like a saddle. You see there's a saddle point. You see what I mean? Not so better. Thank you. So anytime you need a hyperbolic parabola, just call me. Except on the exams. Okay. I will not make you do it, so don't worry. All right, but you should be able to visualize it. So that's a hyperbolic paraboloid. Now, so you see the upshot of all this is that we get a whole variety of surfaces by simply going from equations involving just degree 1 monomials to equations which involve degree 2 monomials and lower. And so that's a very interesting example which kind of indicates the huge variety of surfaces that we have in three-dimensional space. Okay, so that's what we wanted to see in the case of surfaces. Okay, and now we go back to curves. Again, the whole game that we're playing here in three-dimensional space is a kind of interplay between surfaces and curves. And you have a question? What's the equation that makes that? Okay, let's see. So that's actually, I'm glad you asked because otherwise we're kind of missing the punchline. So that's the way this is. So x, y, z. So it's something which should look like. So first of all, it should something which should look like a parabola in this direction. If I look on the x, y, and it should look like. Sorry, this should be hyperbola. This is a parabola, and this is a parabola. So first of all, I want to have z, and I want to have in the y plane. I want to have. Let me try different colors to kind of indicate you. So this green, okay, this green stuff is nothing but z equals y squared. Let's forget about this ABC, the coefficients. We can divide by the coefficients later. I'll just write down the rough formula for it. So this is equal y squared. So that should be part of the equation. This one, right? This is like a parabola. I still haven't erased it. It's right there. What else do we have? We have this part of the picture, which is also parabola. This one is, but it lies in. So this one was in the zy plane, and this is going to be in the xz plane. You see, in the xz plane. Maybe I didn't draw its coordinates nice. Now I can do it slightly. So like this. I'm actually drawing it like this. So that's the z equals negative x squared. And so what it means is that you should have z, right? You should have z, you should have negative y squared, and then you should have x squared. That's what it should be. But because see, what I did is, if I set x equals 0, I get this one. So I get this equation, z equals y squared. And if I set y equals 0, I get z is equal to minus x squared. So that's all good, right? And so finally, if I set z equals some constant, I'm going to get hyperbolas. So that's roughly the equation. I'm not being precise, but this is roughly the equation. So it has a z and it has x squared and y squared, but it's opposite signs. Okay. Now, so the next topic that we'll discuss is general curves, more general curves in space. Okay. So more general curves in space, and again, just like for lines, we parameterize them instead of writing equations. Because now the curve has dimension of the curve is 1, right? So that means we need one parameter, but two equations, because the curve lives in three-dimensional space. So each time we write an equation, the dimension drops by 1. It has to drop from 3 to 1. Therefore, we have to write two equations. But if we use parameters, we need only one parameter. So it's more economical to use parameterization instead of writing down equations. So we introduce a new auxiliary parameter, which usually we call it t, but you don't have to. We can call it s or theta, whatever letter you like, just as long as it's different from the three variables x, y, z. And we write x equals f of t, y equals g of t, and z equals h of t. And of course, we recognize two special cases here. One special case is like this. When you don't have the third equation, the third formula, you only write x equals f of t and y is equal to g of t. That would be a parametric curve on the plane. And we also recognize as a special case the case of a line, where f of t is a linear function, and so are g and h. So in a sense, when we are getting lines in free space, we are also doing the simplest possible parametric functions, f, g, and h, the functions which involve only the constant term and the degree 1 term in the coordinate t. Now, there's one terminological issue which I want to emphasize. When I say equations, I mean equations just involving x, y, and z. You see, because someone can say, well, this also looks like an equation. So what do I mean when I say you need one parameter or two equations? Here I'm actually writing down three equations. That's a terminological issue. I don't think of this as equations, because an equation is something which is a constraint on the variables which are given to you. And this formula involves not only the coordinates which are given, x, y, z, but also some auxiliary coordinate. Okay? So these are not equations. Well, they are equations in some sense, but these are not what I mean by equations. By equations, because they involve t, an additional variable, or what we call parameter. You see, that's why I like to think of it as parameterization. I parameterize x, I parameterize y, I parameterize z. I'm not writing down equations on x, y, z. An equation, on the other hand, is like this. This is an equation. This is an equation. It only involves x, y, and z. There are no additional variables, like t. You see, that's the difference. So is that clear? So don't be confused when I say equation. I don't mean formula like this. I mean formula like this, which involves only the given. Now, someone can say we can actually interpret this as an equation, but on 4 variables, because you can think of this now as a system of equations on variables x, y, z, and t, which is actually another way to think about this. In other words, instead of starting in three-dimensional space and trying to parameterize a curve by one parameter, you can think that what you are doing is that you are working in a four-dimensional space, and you are imposing 3 equations. Because you can look at the four-dimensional space with coordinates x, y, z, and t, and then you can impose these equations. And you see, everything is consistent, because this way you start with a four-dimensional space and you impose 3 equations. So what's the dimension of the object? It's 4 minus 3, because now there are 3 equations, which is 1. So it's all consistent. You get again 1 as the dimension of your object. But I prefer not to think of this expression as a system of equations in a larger dimensional space, namely 4-dimensional space. I would rather prefer to think of this as a way to parameterize my curve by this auxiliary parameter, auxiliary coordinate. Any questions about this? This is really a terminological issue, but I wanted to emphasize it because I keep saying parameterization, equations, and so on, and so I do realize that it could be confusing. Okay. So what can we do with this more general? What can we do with this more general parametric curves? Well, we try to recall what we did with parametric curves on the plane, and we try to do the same thing here. And one of the things we did was we wrote down equations for the tangent lines to these curves. And that's what we like to do for curves in three-dimensional space. So let me do it by way of doing an exercise. For example, find parametric equation to the curve. Sorry, parametric equation. I skipped 2 words of the tangent line. Of the tangent line to the curve given in parametric form as follows: x is equal to 1 plus 2t, y is equal to 1 plus t minus t squared, and z is equal to 1 minus t plus t squared minus t cubed. Okay? At the point 1, 1, 1. So how to do this problem? The first thing you need to do is to check whether this point actually belongs to this curve. You see, in this case it clearly does, right? Because this point corresponds to the value t equal 1. Sorry, t equals 0. If t is equal to 0, we get 1, 1, and 1 for each x, y, and z. So this, of course, is a necessary condition, because if it's not satisfied, if there's no parameter t for which you get precisely the coordinates, it means that there's a misprint in the problem. We saw that. you cannot really do it. It's not self-consistent. So the first step is to find the value of t. Step 1 is to find the value of t which corresponds to this point. And the way you find it is by solving the equation. For example, here it will be 1 plus 2t is equal to 1, which gives you t is equal to 0. And then you hope, you expect that if the problem is correct, that if you plug that solution to the formulas for y and z, you will get the right values. In general, it could be that there's more than one solution that you get from the first equation. So then you have to find which one will correspond to this point. In other words, for which value of t you will actually get that particular point. It could happen also that there are two different values of parameter t which give you the same point. That's called self-intersection. We've seen that when we were graphing curves, especially by using polar coordinates. So that's also possible. But if that's how it happens, then the question would be find parametric equations of the tangent lines, not just tangent line, because in this case there will be two different tangent lines, right? This one and this one. So the question indicates that actually this point is not a point of a self-intersection, but rather it's a point like this where you actually have a well-defined unique tangent line. Okay, so that's step 1 to figure this out. Step 2 is to write down the equation of the line. And now we have to remember what information we need to write down the parametric representation for a line in free space. We need a point and we need a direction vector. And fortunately, we already have a point, 1, 1, 1. We already have the point. So we need the direction vector for this line. And the direction vector is going to be a tangent vector to this curve. And we find it in the same way in which we found it for curves on the plane, by taking derivatives. Of our functions for this value. So in general, the formula is that you take f prime of t0, g prime of t0, and h prime of t0, where t0 is your value. Right? So we simply have to differentiate each of the three functions and substitute. Okay, so let me take 1 minute because there's one important point, and I don't want to lose it. So you see, your curve is already given by parameterization of some variable t. And now you're going to write an equation for a tangent line. A tangent line is a different curve. So you should use a different coordinate to parameterize it. Use a different coordinate for the tangent line. Use a different parameter. Usually, we can utilize the letter s, say ts, but you can use whatever you want. So for example, in this particular case, if you take the derivatives, the value of the derivatives at t equals 0, you will get 2, 1, and negative 1. And so the equation of the tangent line is going to be 1 plus 2s, 1 plus s, and z is 1 minus s. These are the equations of the tangent line. Okay, so we'll continue on Thursday.